Thank you very much. Yeah, so as Neil said, my name's Simon. I'm a site reliability engineer at Giant Swarm. For those of you who don't know us, our main product is managed Kubernetes environment, and it's built on top of Cluster API. And then we deploy this on top of multiple providers, usual cloud providers. We do on-prem as well. We've been doing this for, I think, a little over 10 years now. And I've been there for quite a while as well, a good few years. So hopefully I'm somewhat qualified to speak to you about this today. So just what we're going to cover today, have a quick intro and overview for those of you who don't know what it is. Then we're going to talk about why Cluster API specifically, and then we'll have a look at it in practice as well. Hopefully the demo will go well. We'll see how that goes. So far in practice, it's gone quite well. We'll see how things go with demos. And then at the end, just a quick wrap up, and I've got a few resources for you as well. So before we get started, it's a little bit of audience interaction for you to make sure you're all still awake. So if you're using Cluster API in production, do you mind putting your hands up? Anyone at all? Excellent, that's a good start. That's what I was hoping for. This is looking good. So how about if you've experimented with it or you know of it but haven't used it in production? Okay, and those who have no clue at all, nothing wrong with that. Excellent, that's the distribution I was hoping for, not the other way around. Okay, so let's first jump into the overview and just see how it fits into the Kubernetes ecosystem. So I've heard this mentioned a few times today, day one and day two operations. You've probably all heard of the terms before, and it's just generally talking about lifecycle management of software, not specifically Kubernetes. The definitions predate Kubernetes by a long way, but it still applies really well. And so day one operations are just generally about deploying the thing and getting it up and running. And then day two is managing the life cycle, so the ongoing maintenance burden of keeping that thing, whatever it is, running. And so in the case of Kubernetes clusters, we're talking patching, upgrades, scaling, and also the decommissioning of the clusters at the end of the day as well. So cluster creation isn't easy. If you've had a go at Kelsey Hightower's Kubernetes the hard way, you know this, you've experienced that, because behind the scenes there's a lot of different components that are involved in coming together before you end up with a functional cluster that you can use. So you've got to have some kind of networking, which if you're on AWS is going to be a VPC, or if you're on-prem is just a basic subnet. And you need other network equipment like load balancers, and then where you deploy, that's really going to differ. Depending on the provider, you might need some kind of identity management, so roles and policies. And at the end of the day, a cluster is just a bunch of virtual machines that are all working together. So you need these virtual machines, you need the compute to be provisioned. And for each of these VMs that you have, they've got to be provisioned correctly and configured. So Kubernetes components all communicate using TLS, so you have to deal with certificate management. And so to do that, you have to bootstrap a certificate authority, use that to issue certificates, and then those are obviously put in the right places. And then finally, talking of bootstrapping, you've also got to bootstrap your cluster as well. So that's going to involve bringing up etcd and initializing the control plane. And then once that's healthy, then obviously you've got to join your worker nodes to it. So there's a significant amount of orchestration going on before the cluster is even usable. So building a cluster isn't easy, and to be honest, neither is maintaining it either, because there's a lot of things you've got to think about. Specifically security and vulnerability patching. There have been quite a few talks today that have mentioned this kind of thing. Very important. Each Kubernetes release has bug fixes for vulnerabilities. So if you're running an outdated cluster, then you're leaving it open to known exploits that anyone can take advantage of. So I think Adrian mentioned earlier, back in April, there was a pretty serious vulnerability with the Nginx ingress controller. And the statistic I like or dislike is that it affected roughly half of all internet-facing clusters, which is a huge number. And I know this isn't a core Kubernetes component, but it's a good demonstration of the impact that these vulnerabilities can have. So stability and performance are also very important considerations. So regular Kubernetes updates deliver you bug fixes and performance improvements across your clusters. So if you run outdated versions, then you risk degraded performance or maybe unpredictable behavior under load. And the only way to get these optimizations and these fixes is through keeping your clusters up to date with the newer releases. Then from a compliance and support standpoint, if you're running on the major cloud providers, most of them will only support the last 3 minor versions of Kubernetes. So there's quite a lot you've got to keep up with. I can't remember what the release cadence is now, but you don't have that long to upgrade. And so running an older version, it might mean you end up falling outside your provider support window. So you could potentially, depending on your contracts, lose vendor support. Or if you run in a regulated environment in some way, then you could be out of compliance there as well. And it's important to note that these first 3 points also really apply to not just the cluster, to Kubernetes, but to the OS that you're running on. So that's something else you've got to think about as well. And then looking beyond the patching and updating, you have just general lifecycle management, so things like scaling and fault recovery. So you might need to scale your clusters up or down based on your workloads. So there's got to be some kind of tooling there that can do that for you. And similarly, when your nodes fail, if they become unhealthy for whatever reason, obviously this gets detected and they need to be replaced quickly so that your cluster stays healthy. And so to achieve this over the years that Kubernetes has been around, there have been a lot of different tools that have been developed that can help with this. Bunch of different logos here, you probably recognize some or all of them, but we're going to be looking at the 3 turtles over here on the left-hand side, which is the cluster API logo. If you don't want to use any of these tools, of course, you don't have to, no one's making you do that. You can do it all yourself. You can write your own controllers, or you can use some bash scripts to do this. But I mean, to be honest, speaking from past experience in some of these areas, it's not a very good idea unless you like causing yourself pain, so just don't do that. So, as we've just seen, there were quite a few different tools there, and they're all doing roughly the same thing at the end of the day, but we're here talking about Cluster API. So let's have a look at how it helps us solve some of those challenges. So, as I said, you don't have to use it or any of the others. You can do it all manually. You can use what I would call ClickOps or some scripts to do it, but really would heavily discourage this approach because manual cluster creation will cause you to end up with snowflakes, and these end up unique and hard or potentially even impossible to reproduce them, which will then also lead to inconsistencies between your environments. So say, for example, if you have a dev cluster and somehow it's differed and it's different from your production cluster, you deploy your app in dev, works perfectly there, but then how can you trust if your clusters are different that it's actually going to work properly in your production cluster as well? And then if you make ad hoc changes, so you do kubectl edit, then this is going to cause configuration drift to happen, and it makes it difficult or impossible again to reconcile the desired state of the cluster, the actual state of the cluster with the desired state. And generally doing anything manually complicates things, producing potentially more downtime than you need. And same thing, guys, if you're scaling your cluster, having a human in the loop does really slow things down, and just to be honest, relying on humans in general increases risk and reduces your reliability. And so doing it in automated fashion is obviously vastly better. So Cluster API, this is straight out of the handbook, uses Kubernetes-style APIs and patterns to automate lifecycle management. So obviously then the goal is to automate everything, or as much as you can anyway. And because we're using Kubernetes, Cluster API does this using controllers, and these manage your cluster provisioning, configuration, upgrades, and teardown at the end. And so there's no manual intervention or any scripting involved whatsoever. And because the cluster is defined in YAML, the actual state of the cluster is continuously reconciled with the desired state against these YAML documents. And so if any drift does happen to the cluster for some reason, the controllers will correct it automatically because they know what it should look like. And this then makes your clusters reproducible and predictable, so the exact opposite of snowflakes. And using this approach as well, using Git, GitOps workflows allows you to obviously store your YAML in Git. And so this gives you a single source of truth with version history. And so any changes to those documents, if there's a problem, can be rolled back. They can be audited. And so if it's 3 o'clock in the morning, you get paged, you can go and use a Git blame and figure out who did the thing that caused you to be woken up in the first place. So I guess to talk about it, we kind of need to understand some basic concepts first. So first off, the most important part, we start with the management cluster. And so this is just a normal Kubernetes cluster running some controllers, and it's responsible for managing any number of workload clusters. And a workload cluster is a Kubernetes cluster and whose lifecycle is being managed by a management cluster. And so these workload clusters are what you give to your end users where they would deploy their applications. And the management cluster itself is also a special kind of workload cluster, but we don't really have time to get into that today because that's a bit of a complex subject. So in order to provision these clusters, as I said, in the management cluster, there are several different controllers that are going to be running there. One of these is the infrastructure controller. So this is responsible for provisioning of the infrastructure components, so things like your networking and your virtual machines. And it's a bit of a bridge between your YAML and the real world where the physical infrastructure gets created. And then you have a control plane controller, which, as the name implies, looks after the control plane. And it's responsible for keeping that healthy and making sure that it's running. And then there's also, finally, the bootstrap controller, because you've got to turn these virtual machines that you create into working cluster nodes. So, as with everything in Kubernetes, it's all custom resources. So the primary one that we're interested in here is the cluster custom resource, not particularly well named, unfortunately. So this represents a logical cluster, completely provider agnostic. So every cluster you have, regardless of where you deploy it, what platform it's on, is going to have a cluster. And this cluster object then references the infrastructure cluster, which is the provider-specific component. So in this case, we're talking AWS or Proxmox. And this handles the actual provisioning and the management of the resources on that provider. So you can think of like the cluster as saying, I want to have a cluster, and then the infrastructure cluster does the interfacing with the APIs underneath and builds what you've asked for. So every cluster obviously has to have a control plane of some type, and this is managed by the control plane provider. And it's responsible for managing the machines which make up the control plane, make sure the control plane is healthy and running, and it will also handle upgrades and scaling of the control plane too. If you want to go up, if you need more replicas, it can do that. The most common provider is the kubeadm control plane, but there are others as well that exist. So, we need some workers as well for the cluster to be useful. So these are managed by what's called a machine deployment. And a machine deployment is a little bit like a deployment of a pod. It contains information such as the number of replicas, the update strategy, and the infrastructure template or the machine template that the machines themselves reference. And then underneath that, you have a machine set, which is very, very similar to a replica set. And it handles the actual management of the running machines and will create and destroy them to ensure you have the desired number of replicas or workers that are actually there that are required by the machine deployment. And so when you apply all of these resources to the management cluster, the controllers stitch them all together and you end up with a complete cluster which looks a little bit like this. There's quite a lot that's left out of this in order just to focus on the core components here, but it does sort of show how everything is knitted together. And so, given what we know now about Cluster API, it might seem that lifecycle management is now easy. Maybe easier, not easy. But in reality, it's a sophisticated tool, it's complex, and so it requires initial investment and buy-in, and obviously you've got to learn what you're doing with it. But this upfront effort really pays off because Cluster API lets you manage multiple clusters across lots of different environments, be it on AWS or in your home lab, and it keep them upgraded, consistent and healthy at the same time. So, we've looked at some of the basics and sort of a bit of an idea as to how it works. Obviously, as with anything, there's potential pitfalls and stumbling blocks that you will probably run into at some point, so we should talk about those. So some of these, I had a chat with some of my colleagues at work and tried to gather some different viewpoints from different users. Version skew can be a really big problem because each Cluster API release will only support a specific range of Kubernetes versions, and the same also applies to your infrastructure controller and the control plane providers as well. So you've got to ensure that all three of these, so the Cluster API version, the controller versions, and Kubernetes itself, all stay within compatible boundaries, because if they don't, then if you fall outside those, you can end up with reconciliation failures or potentially unmanaged clusters as well. I said that all providers are not equal. What I mean by that is that obviously they're all doing the same thing, they're building you a cluster, but they're all getting there in very different ways because the underlying infrastructure is quite different in each case. EKS, so Amazon's managed Kubernetes, in my experience is very slow to delete clusters. Don't know if it's just me, but I've always found that. VMware Cloud Director is very slow to do absolutely everything. And vSphere, as we'll see in the demo shortly, I found to be generally pretty fast to do everything, so complete opposite to Cloud Director. As we talked about earlier, you've got multiple different controllers, and they're all responsible for different parts of the cluster's lifecycle. And so this is obviously done to improve modularity, but it makes debugging sometimes quite difficult, because when something breaks, you've got to know where exactly to look. So which controller is responsible, and then go off and go log diving. And really knowing where to look can be quite difficult at times. And there is no single pane of glass, they're just a bunch of different pods. So in practice, I found the only way to improve with this is just through experience and knowing where to look. On some of the previous slides, I've mentioned machine templates, and the machine template is responsible for defining how the machines that make up your cluster look. So how much memory they have, like sort of CPU specs, disk space, this kind of stuff. But these machine templates are immutable. So if you want to increase, let's say, the amount of memory that your workers have got, you actually have to create a brand new machine template with your updated spec and a different name. You apply that to your cluster, and then you have to change the machine deployment to reference the new template, and only then do your nodes actually get updated. There are ways around this, but I haven't really got time to cover those here today. And also, it seems a little odd to say it about a cluster, but I think management clusters, for me, can be a single point of failure. I say it sounds odd because they're a bunch of different machines, but if you treat them as a single entity, and especially given how important a management cluster actually is, there's a bunch of different ways it can break. And so if you did have a catastrophic failure and you can't recover it, then what happens then is that your workload clusters then become unmanaged. So they're frozen at that point in time. They keep working, but you can't do anything with them. You can't scale them or anything. And so it's very important to make sure your management cluster gets backed up so it can be restored if there's a problem. Another area of concern with management clusters is, by design, they have access to all the workload clusters that they manage, because that's how they access them to provision them. But that means that if a bad actor gets access to your management cluster, he's then compromised all of your clusters. So the blast radius is pretty big with something like that. So security of your management cluster is extremely important, even more so than any other, I would say. So that's all the kind of rough edges, or not all of them, some of them anyway. I've got a short demo which should show how easy it is to scale a cluster using Cluster API. The original plan for this was to do the demo in my homelab, which runs on Proxmox, but I'm moving house next week, so it looks a bit like this at the moment. So instead, I'm going to use one of our test environments from work. It'd be based on vSphere, but the same fundamentals still apply because it's Cluster API underneath. Quite tight for time with this, so if you've got any questions, please hold them for the end or come and find me for a chat afterwards. I can go on about this stuff for ages. Let's just change to that. Yep, how does that look size-wise? Is that all right? Okay, so we've got a small cluster here. We've got 2 workers. And let's say we want to scale it up a bit. So let's do, we can see we've got also, that's the machine deployment there, which desired to current 2. So that's ready to go. So what we're going to do is we're going to scale it up. Let's see if we can find it in my history. There we go. Nope. Okay, so that is as simple as, no, it's not. This is what I get for trying to do it over my shoulder. So that is quite simple. We go down here to the number of replicas, which currently is set to 2. Hopefully you can all see that's a bit low down. And then we'll change that to 10. No, we won't. Yep, change that to 10. So I'm going to save that. So what's happening now is the controllers are going to go off and reconcile stuff. Let's watch what's going on. It's would have been much easier when it's on the screen in front of me. Sorry, my bad. There we go. Okay, so the more observant among you there will have noticed that I did exactly what I told you not to do. I use kubectl edit. Normally what I would do is I would make a PR to the GitOps repo, that gets merged, and then Flux or Argo will deploy it to the cluster, and then we end up at this point. But this, I don't really have a lot of time for this demo, so I'm doing it the quick way. This really is a case of don't do what I do what I tell you. So we can see here we've got nodes, we've got machines, and we've got vSphere VMs down the bottom here. So what I've done, when I changed that machine deployment to have more replicas, what's happened is the machine deployment controller has seen that change, and it has then scaled up the underlying machine set, which manages the machines themselves. And then that machine set scaling up has caused the creation of new machine objects, which is what we can see here. So for each machine that gets created here, we've got a couple of important things that are going on at the same time. These are Ubuntu VMs that we've got here. So they're created using Cloud Init. So the Bootstrap controller knows this, and it's created a Cloud Init script for them to provision them. And then the infrastructure controller at the same time has provisioned a virtual machine down here, and it also injects the Cloud Init script into those VMs. So the VM boots, the kubelet runs, and it contacts the API server. As part of that Cloud Init script, it was given a Bootstrap token, and it registers with the API server. And initially, it goes not ready. Then you get a bunch of things happening at the same time. The machine controller links the node to the underlying VMs, so you know actually which piece of physical infrastructure is responsible for it. And your daemon sets, your critical system pods are going to start running on those nodes. So your kube proxy, your CNI, whatever you might be using. And then when all these things have happened and the node is reporting healthy, it turns ready, which we can see we've got now. And so there, we've used Cluster API. We scale from 2 to 10 nodes. I wasn't watching the time this time, but in my previous tests, it's taken anything like 80 to 90 seconds. And so all those nodes within 90 seconds are ready to accept workloads. And it really is that simple. So let's flick back to the demo, because I am quite short on time. Where are we? Sorry, back to the slides, rather. OK, so let's skip on just to wrap things up. So I think it's pretty safe to say that cluster lifecycle management is complex. There's no getting away from that. You can't avoid it, whatever approach you use. Manual approaches, you end up with drift and unreproducibility, and your operational toil goes up, and your employee happiness goes down. Cluster API doesn't hide that complexity, but it does abstract it, so wherever you're deploying, it's consistent. It's not magic. There are still problems, as we saw. Things like version skew and controller sprawl make it more difficult, and they will catch you out because everyone gets bitten at some point. There's a lot of different things you've got to think about. But I think I'd sum it up by saying that, in my opinion, I think Cluster API doesn't remove your complexity, but it organizes it and makes it somewhat easier to work with. So finally, just a couple of resources here for you. That QR code will take you to that repo, which is where all the resources for this talk are, the slides, the manifest that I've used to create the clusters. And if you are interested in Cluster API, if you want to read a bit more, the book, there's loads of information there. It's really, really helpful. I thoroughly recommend reading through that. And if there's no one else taking photos of slides, perfect. That's it. Thank you very much, everyone.